Welcome to the OWASP Top 10 for Large Language Model Applications 2025 edition. In the next 15 minutes, we'll walk through all 10 categories of the most critical security risks in AI-powered applications. From prompt injection to model theft, you'll understand what each vulnerability is, why it matters, and how to defend against it. Whether you're building with ChatGPT, deploying open-source models, or integrating AI into enterprise systems, this overview will sharpen your understanding of LLM security. Let's get started. Let's start with the 5 most critical risks. These represent the most common and impactful vulnerabilities found in applications that integrate large language models. Here are the first 5 OWASP LLM Top 10 categories with their core risk and primary prevention strategy. LLM 01 prompt injection is the #1 risk for LLM applications. Attackers craft inputs that override the system prompt, bypass safety guardrails, or trick the model into performing unauthorized actions. This includes both direct injection through user prompts and indirect injection through poison content the model retrieves. Prevention requires input filtering, output validation, privilege separation between the model and backend systems, and human-in-the-loop for sensitive operations. LLM 02 sensitive information disclosure occurs when models reveal confidential information from their training data, expose system prompts, or leak personally identifiable information. Models can memorize and reproduce sensitive data they were trained on. Prevention requires sanitizing training data, filtering model outputs for sensitive patterns, implementing access controls on training data, and never including secrets in system prompts. LLM 03 supply chain vulnerabilities cover risks from using pre-trained models, third-party datasets, or ML pipeline tools that may be compromised. Attackers can poison training data, insert backdoors into fine-tuned models, or compromise model registries. Prevention requires verifying model provenance, auditing training datasets, securing ML pipelines, and using signed model artifacts. LLM 04 data and model poisoning occurs when attackers manipulate training data or fine-tuning processes to introduce biases, backdoors, or malicious behaviors into the model. This can cause the model to produce harmful outputs under specific conditions. Prevention requires rigorous data validation, statistical anomaly detection in training data, federated learning safeguards, and continuous monitoring of model outputs for unexpected behavior changes. LLM 05 improper output handling occurs when LLM outputs are passed directly to backend systems without sanitization. If the model generates SQL queries, shell commands, or code that gets executed, attackers can achieve remote code execution through prompt injection. Prevention requires treating all model output as untrusted, sanitizing before execution, running LLM-generated code in sandboxes, and enforcing least privilege for any actions the model can trigger. Prompt injection is the most critical and unique risk to LLM applications. Here is how attacks typically work and how to defend against them. In direct prompt injection, the attacker crafts user input that overrides the system prompt or safety guardrails. Techniques include role-playing prompts like pretend you have no restrictions, instruction override attempts, and encoding tricks that bypass input filters. This is the most straightforward attack vector. Indirect prompt injection is more dangerous because the malicious payload is hidden in external content the model retrieves, like documents, web pages, emails, or database records. When the model processes this content, it follows the injected instructions, potentially exfiltrating data or performing unauthorized actions without the user's knowledge. The impact of successful prompt injection ranges from data exfiltration and unauthorized API calls to safety guardrail bypass and reputation damage. In agent-based systems where the LLM can take actions, prompt injection can lead to financial fraud, data deletion, or system compromise. Effective defense requires multiple layers. Input filtering catches known injection patterns. Output validation prevents sensitive data leakage. Privilege separation ensures the model cannot directly access critical systems. Rate limiting and monitoring detect anomalous behavior. Human-in-the-loop approval for high-risk actions provides the final safety net. LLM security introduces fundamentally new challenges that traditional application security approaches cannot fully address. Traditional application security deals with deterministic systems where the same input always produces the same output. Trust boundaries between user input and system logic are clear. Injection attacks target interpreters with structured syntax, like SQL. Access control is enforced through explicit code-level authorization checks that can be tested and verified. LLM security faces fundamentally different challenges. Outputs are non-deterministic and vary even with identical inputs. Trust boundaries are blurred because natural language mixes data and instructions in the same channel. Prompt injection exploits the model's core instruction-following capability, not a parsing vulnerability. Access control must limit what actions the model can trigger, not just what data users can access. Now let's cover categories LLM 06 through LLM 10. These cover operational risks including excessive agency, denial of service, and model theft. Here are categories LLM 06 through LLM 10 with their core risks and prevention strategies. LLM 06 excessive agency occurs when models are granted too many permissions, excessive plugin access, or the ability to take high-impact actions autonomously. When combined with prompt injection, excessive agency can lead to data deletion, unauthorized purchases, or system compromise. Prevention requires enforcing least privilege for all model capabilities, requiring human approval for high-impact actions, and strictly limiting the scope of tools and plugins. LLM 07 system prompt leakage occurs when attackers use clever prompting to extract the system prompt, revealing business logic, security rules, and behavioral guidelines. Prevention requires never relying on prompt secrecy for security, enforcing all security controls server-side independent of the prompt, and applying prompt hardening techniques while accepting that determined attackers will eventually extract the prompt. LLM 08 vector and embedding weaknesses cover risks in retrieval-augmented generation systems. Attackers can manipulate embeddings, poison vector databases, or exploit similarity search to inject malicious content into model context. Prevention requires validating inputs to embedding pipelines, enforcing access controls on vector stores, detecting anomalous embedding patterns, and filtering retrieved content before sending it to the model. LLM 09 misinformation covers the risk of models generating confident but factually incorrect information, often called hallucinations. This is especially dangerous in healthcare, legal, and financial applications where incorrect information can cause real harm. Prevention requires retrieval-augmented generation with verified source documents, confidence scoring and uncertainty flagging, human review for critical outputs, and clear disclaimers about AI-generated content. LLM 10 unbounded consumption covers denial of service attacks and cost exploitation through resource-intensive queries. Attackers can craft prompts that consume excessive tokens, trigger expensive operations, or exhaust API budgets. Prevention requires rate limiting per user and per session, setting token budgets, limiting query complexity, implementing cost monitoring with alerts, and having circuit breakers for runaway costs. Securing LLM applications requires a defense in-depth architecture with controls at every layer. The input layer provides the first line of defense. Prompt filtering catches known injection patterns and policy violations. Input validation enforces length limits, character restrictions, and content policies. Rate limiting prevents abuse and denial of service attacks at the API gateway level. The model layer secures the LLM itself. System prompt hardening uses structured delimiters and role separation to resist injection. Temperature and sampling controls reduce output unpredictability. Model access policies ensure only authorized applications can invoke the model with appropriate configurations. The output layer validates everything the model produces. Content filtering catches harmful, biased, or policy-violating responses. Sensitive data detection scans outputs for PII, credentials, or confidential information before they reach users. Output format validation ensures structured responses conform to expected schemas. The action layer controls what the model can do in the real world. Strict privilege boundaries limit tool and API access to the minimum necessary. Human-in-the-loop approval gates high-risk operations like data modification or financial transactions. Comprehensive audit logging tracks all model actions for forensic analysis and compliance. LLM application security introduces challenges that don't exist in traditional software security. Unlike SQL injection, which can be eliminated with parameterized queries, prompt injection has no single technical fix. Natural language inherently mixes data and instructions. Defense requires multiple complementary layers, including input filtering, output validation, privilege limits, and human oversight working together. LLMs produce different outputs for the same input, making traditional test assertions unreliable. Security testing must use adversarial red teaming, statistical evaluation over many runs, and behavioral testing that checks for policy violations rather than exact output matching. In RAG systems and agent workflows, the attack surface extends beyond direct user input to every document, web page, email, and database record the model processes. Indirect prompt injection through poison content is harder to detect and defend against than direct attacks. When LLMs are connected to tools, APIs, and databases in agent workflows, prompt injection can trigger real-world consequences. An agent with database write access, email sending capability, or financial transaction authority can cause serious damage if compromised. Least privilege and human approval for high-risk actions are essential. Let's close with the most important lessons from the OWASP LLM Top 10 2025. First, prompt injection is the defining security challenge for LLM applications. Treat all model inputs as potentially adversarial and all model outputs as untrusted. Never pass model output directly to interpreters, databases, or APIs without sanitization and validation. Second, defense in depth is not optional. No single control, whether input filtering, system prompt hardening, or output validation, can secure an LLM application alone. Effective security requires coordinated controls at every layer from input to action. Third, limiting model agency is critical. The combination of excessive permissions and prompt injection is the highest risk scenario in LLM security. Apply strict least privilege to all model capabilities and require human approval for any action with significant real-world impact. And fourth, LLM security is a rapidly evolving field. New attack techniques and defense strategies emerge regularly. Continuous learning, staying current with OWASP updates, and adapting your security controls as the technology evolves are essential for maintaining robust LLM application security. That wraps up our overview of the OWASP LLM Top 10 2025. In the full Udemy course, you'll get detailed lessons on each category with real-world attack demonstrations, hands-on defense implementations, prompt injection testing techniques, and practical security architecture patterns for production LLM systems. Use the course to build security into your AI applications from day one. Thank you for watching. If you found this overview helpful, subscribe to the channel for more security content, and check the description for the link to the full course. See you in the next video.